Hello scholars, welcome. Mr. Hinkle here. In this lecture we're going to talk about absolute or numerical age dating, how we actually put the number of how old a rock is on that specific rock. So we'll define what it is, and then we'll get into the process of radioactive decay and how radiometric age dating actually works. So what is, excuse me, what is numerical or absolute dating? Well, it's a quantitative, meaning quantity or number. Excuse me. Okay, I think I'm good. That can put an absolute age date, a specific amount of time of how old a rock is. So if we know how old it is, we know how old the Earth is, and we know what today is, we can say how old this rock is. Now, this comes out of a technique developed in the late 1800s called radioisotopic dating. Another word for this is radiometric, that now with this new technique can assign time units in years to mineral grains within a rock. So let's put a title up here. Numerical absolute age dating. Excellent. Okay. So numerical values don't matter on other rocks. You have a rock in situ and you find it and you grind it up and you put it through this machine called a mass spectrometer, and it measures all of the different elements that are inside of the rock. Elements, you say. Okay, well, what's going on with the elements? Well, in order to know that, let's talk a little bit about chemistry. So, periodic table of the elements. Atoms, the fundamental unit of life, or of matter, excuse me, that cannot be indivisibly split, formed of protons, neutrons, and electrons. Well, each atom forms an element defined by the number of protons in its nucleus. But there are variations for each element based on the number of neutrons, which give us different isotopes. So here's the example. Carbon. Every atom of carbon has 6 protons in its nucleus. But there's different variations of carbon. You've got carbon 12 with 6 neutrons, carbon 13 with 7 neutrons, and carbon 14 with 8 neutrons. Now the special thing here is that carbon 12, stable, lasts forever. Carbon 13, stable, lasts forever. Carbon 14, radioactive, which means it breaks down over time and it changes into different elements. What? I know. Wild, right? But it is this process of radioactive decay, which I think I have here. Yep, great. This process, right? Because most isotopes are stable. They'll remain in the same stable isotope until, some supernova explosion happens. But some isotopes are unstable, meaning they undergo radioactive decay, where uranium can go through a series of different reactions over time and turn into lead. This is a big one. Uranium to lead. This happens. An isotope of uranium, unstable, over long periods of time, breaks down and becomes lead. So this process of radioactive decay allows us to calculate how old a rock is because these happen at known constant rates. Definitions. The time needed for half of the parent atom to decay into the daughter is called the half-life. So we're measuring the amount of half-lives. We've got uranium to lead, different isotopes, 238 to 206, 235 to 207, potassium, argon, rubidium to strontium. The parent decays into the daughter. Half of the parent decays into the daughter in 4.5 billion years, so uranium to lead, really good for measuring old rocks. goes like this. Let's talk about half-lives. This is how we put actual ages on rocks. If you've ever wondered, how do we know the Earth is 4.6 billion years old? Well, rocks fell out of the sky and landed on our Earth. They're called meteorites. And then we grinded them up, we pushed them through a mass spectrometer, and we measured the unstable isotopes through this process. So when a rock solidifies, at time 0, it's 100% the parent atom. Half of it goes away in a half-life, which means that after one half-life, it's 50-50. You take half of 50%, that's 25%, meaning that the remaining is 75%. Half of 25% is 12.5%. Half of 12.5 is 6.25. Half of 6.25 is 3.125. I don't know, I forget the exact number of that, but it's half, so on and so forth. Where does that half go? Into daughter. So as time goes on, there's less and less parent, more and more daughter, and this is what the mass spectrometer measures. It measures the relative proportions of parent to daughter. So, another example. When magma is hot, it solidifies. So all of the isotopes are the blue ones. There's 16. One half-life passes, half of the blue turn red. So that means it's 8 and 8. Now there's 8 remaining blue. Half of the 8, which is 4, turn red, which means the remaining blue are 4. So if you were to take a rock you've never seen before and count up all the reds and the blues, and you counted 4 blue and 12 red, you would say it's 75% red, 4% blue, 4% parent, 75% daughter. And if that's the case, 25% parent, 75% daughter. Maybe I said that, I got a little confused. Then you could say 2 half-lives have passed. And you know the decay constant, say it's 4.5 billion years. Well, those 2 half-lives would say that that rock is 9 billion years. Okay, got it. So this is what we do. We take a newly formed rock that deteriorates, that decays over time. We grind it up in the mass spectrometer, measure the relative amounts of parent to daughter, and then apply the decay constant to see the exact age of that rock. So, uranium lead, really good for old rocks because the decay rate, the half-life, takes a long time. Carbon has a relatively short life. Carbon-14 decays very rapidly, a little bit over 5,000 years. So we use carbon dating for recent dates, and we use uranium lead dating for really old dates. Excuse me. And there are other, as we saw from our chart before, there are other isotopes that are important to use for various ages. So this is how. How do we know? How do we know that? My favorite question. Who the heck said the Earth is 4.6 billion years old? Well, it was actually Claire Patterson who was the first to do this technique, applying to meteorites, the Canyon Diablo meteorite in particular, and said, based on uranium lead dating, the Earth is this old. And then we apply it to the geological timescale to rocks of all different types of ages, and we can really refine and hone in and understand the timeline and the history of the events of the Earth within the specific, it's called geochronology of Earth's past. So that is numerical or absolute age dating. Thank you so much, and I'll see you again.